Hello everyone, and thank you for giving me the opportunity to present today. My name is Corey Porter, and I'm excited to share the results of a project that brings modern data science into one of the oldest and most celebrated industries in the world, winemaking. For centuries, the production of wine has been described as a craft and even an art form. But over time, science has played a larger role. From understanding fermentation chemistry to controlling temperature and acidity, today we are taking that scientific integration one step further by asking, can we actually predict the quality of a wine before it is bottled, do so accurately enough to guide business decisions? As I'll show you, the answer is yes, and the implications are game-changing. A predictive capability like this means wineries could make changes early in production, avoid costly surprises, and strategically allocate resources toward their best performing batches. Over the course of this presentation, I will walk you through the business problem, the data we have worked with, the methodologies we have used, the model that we have developed for this prediction, the results achieved, and most importantly, what these results mean for you as stakeholders and decision makers. As we go through this, I want you to think not only about the technical achievement here, but also about the real-world possibilities, faster decisions, higher profits, and more consistent quality in a highly competitive market. In wine production, the difference between a good wine and a great wine can be incredibly small, yet enormously significant in economic terms. Even half a point on a quality scale can determine whether a bottle is sold as a premium product commanding a higher price or as a mid-market bottle with a slimmer margin. The traditional method of determining quality involves human tasters, skilled professionals who evaluate things like aroma, taste, and overall balance. While this is essential, the problem is timing. By the time the tasting panel delivers its verdict, the wine is already bottled, labeled, and sometimes already distributed. At that stage, if the quality score is lower than expected, options are limited. Maybe the winery blends it with a higher quality batch to improve flavor. Maybe they discount it to move more inventory. Both approaches mean lost revenue and potential damage to brand reputation. Now, imagine if we could change that timeline. If we can move quality prediction up to the right moment directly after fermentation, when lab tests are already being done for basic parameters like acidity, sugar, and alcohol content. At that stage, changes can still be made, acidity can be adjusted, sulfates can be added or reduced, alcohol slightly increased, and so forth. This is the heart of the business problem. We need a way to forecast a wine's quality before final production, i.e. before bottling, before labeling, before marketing, before business deals are struck, so adjustments can be made proactively. In other industries, predictive analytics has become a competitive necessity, and we are proposing to bring that same strategic advantage into this industry. If we can do this reliably, the benefits ripple across the entire value chain. For winemakers, the model becomes a decision support tool. It gives them a heads up on which batches are underperforming so they can make targeted adjustments, not by trial and error, but by looking at which chemical properties are driving the predicted quality. For quality control teams, this means that the predictive scoring allows them to focus their most detailed and expensive testing on batches that matter most, i.e. those in the borderline quality range where small changes can make a big difference. For marketers and distributors, this is about planning ahead. If you know 6 months in advance that a batch is likely to score in the premium category, you can begin developing branding campaigns earlier. On the other hand, if a batch is predicted to underperform, you can plan for a different market tier without scrambling at the last minute. Even certification boards benefit. They can use this model to pre-screen batches for compliance, reducing the risk of costly rejections or reclassifications after bottling. In short, this is not just a winemaker's tool, but it is a business intelligence tool for the entire operation, from production to sales. The success of any predictive model starts with its data. We began with the Kegel wine quality dataset, which contained data on red wines from Portugal's Vinho Verde region. However, it became clear early on that this was an incomplete dataset, as it contained only red wines and only approximately 1,600 of them. This meant that our model would have been skewed heavily. However, after digging deeper into that dataset, reading the comments by other users, as well as reading the bio of the person who posted these results, we found out that there was a additional data set to include white wines from UCI machine learning repository from the same region that has all the same statistics, totaling our wine list to just under 6,500 wines. Now, yes, this does mean that our white wines heavily outweigh our reds, but it provides a much more thorough starting point. Each wine had 11 physiochemical lab measurements, things like fixed acidity, volatile acidity, residual sugar, sulfates, alcohol content, and more. And each of them also were given a quality score from trained testers on a scale from 0 to 10. The important thing to note in this distribution of scores, most wines in this dataset scored between 5 and 6. That is typical in a real-world production. Extremes like a perfect 10 or a disastrous 1 or 2 are rare. The concentration in the middle affects how the model learns. It will be best at predicting wines in this common range, but less precise at predicting the extremes. That's a limitation we'll address later as discussing the improvements of this model. As for data ethics, I want to address the practical limitations of using this data. First, all wines in our data set are from the same geographic region of Portugal. This means that our model is tuned to the environmental conditions, soil types, and winemaking practices of that region, making potential vineyards across the world susceptible to variables that are unaccounted for. If we were to apply it directly, for instance, to Napa Valley or to Bordeaux, the accuracy might drop unless we retrain it with data from those regions. Secondly, while both data sets are public and permitted for academic use, any commercial development requires reviewing licensing terms and complying with any citation requirements. This is a key step moving forward if we consider this model for use in an operational adaptation. Thirdly, we have transparency about these constraints, building trust. We are not claiming that this model will work perfectly everywhere, but within its domain, it performs strongly and provides actionable insights. Here, we can see that we once had data from Kegel as well as UCI, providing us with a red list and a white list, which we appended and wrote to a new Excel document, which we then ran through our model. We merged these two data sets, removed a handful of duplicates, made sure that all of their column headers were accurately reported in the same, so that our model would not be confused or drop data that would be important for us in later use. While some variables were strongly correlated, none exceeded thresholds that would cause modeling issues, so nothing needed to be retrained. This preparation ensured that our model would have a clean and complete data set to learn from without distortions caused by missing values or redundant variables. And again, while we could have used the approximately 1,600 red wines from Kegel by including the other 4,000 or so white wines, we have increased the reliability and accuracy of this model by providing it with a not only more complete data set, but with a significantly larger one. The feature important analysis revealed the biggest drivers for predictive quality. The strongest positive predictor was alcohol content. Wines with higher alcohol percentages tended to receive higher quality scores, likely because alcohol enhances things like body, aroma, and flavor intensity. The strongest negative predictor was volatile acidity. High levels produce sharp vinegar-like notes that are generally undesirable in wine. Sulfates had a positive impact, contributing to preservation and stability, which maintain quality over time. And citric acid also played a positive role, adding a freshness and balancing acidity, improving the wine's sensory appeal. These relationships mirror what skilled winemakers already know. However, showing this is helping us to validate the impact and trustworthiness that this model is producing. Here you can see that we have tested multiple regression algorithms to include things like decision trees, random forests, deep learning, gradient boosted trees, and support vector machines. We focused on regression rather than classification because we wanted precise predictions. Exactly what quality scores rather than broad categories like low, medium, or high. Although we did also run AutoModel through our RapidMiner software to get those, we found that they were generally less reliable since so much of our data is focused on scores 5 and 6, skewing our data into the medium category, so it was just generally less reliable. For our data set, we split the data 70-30 into training and validation sets and evaluated models using RMSE, MAE, and correlation matrix. The goal is not just accuracy, but consistency and interpretability, ensuring that you as the stakeholders could trust the results and understand what factors were driving them. Utilizing the support vector machine stood out as the best performer. It achieved an RMSE of 0.681 and an MAE of 0.467, meaning that our predictions were typically within a half a point of the actual score. In practical terms, that's a difference between a wine scoring a 6.8 or a 7.3. Enough to influence its marketing category. Residual analysis showed no systematic bias, though predictions at the extremes were slightly less accurate due to so few examples. Visually, the predicted versus actual scatter plot shows a tight cluster along the ideal prediction line. This is exactly what we expect to see, labeled as just good, sitting somewhere between 5 and 6. So let's look how this plays out in the real world. For winemakers, imagine a batch predicted to score a 5.7. If you knew before bottling that you could slightly increase its alcohol content or adjust its sulfates, the predicted score could rise up to a 6.1, enough to move it into a higher price category, change marketing tactics. And for marketing, early identification of batches predicted above 7.2 allows them to plan for premium campaigns well before bottling. For quality control, a spike in volatile acidity can trigger immediate corrective action, preventing a batch from slipping into a lower marketing category. As for deployment, this is pretty straightforward. The lab results that we have gathered are entered into the model right after fermentation. Predictions below 5 trigger a review, and the oversight committee, consisting of the winemakers, quality control managers, as well as the data analyst on site, decides on next steps. The model is retrained quarterly to maintain accuracy, with alerts set if RMSEs exceed 0.75. This model is well suited for integration into a winery's quality control workflow. We can run predictions as soon as laboratory results are available and do batch scoring. We can flag any batch with predicted quality below 5, and we can retrain regularly. As for governance, an oversight committee, including the winemaker, quality control manager, and data analyst, will review model outputs, assess fairness, and approve updates. The model's accuracy is constrained by the data's scope. I mentioned earlier that this data, one, was incomplete from our initial source, needing to find the second source of our white wine list. However, even with that found, approximately 4,500 wines is not enough to make this a foolproof model. We need a few things. We need to expand the scope of testing to be worldwide, or if the winery that would like to use this model is located in a specific region, then we can train that model for this specific region, just as this model has been trained specifically for Portugal. Missing things like the vintage year prevents adjustments for seasonal climate variation, and keeping in mind that because we are going off of human taste tests and they are remaining anonymous, we must keep in mind that there is subjective bias that will never be able to be controlled. However, incorporating things like vintage data, expanding to international data sets, and combining chemical analysis with tasting notes for a more rich, predictive model over the course of the next growing and producing season will help us greatly. In conclusion, we have shown that machine learning can predict wine quality with moderate accuracy before bottling using only lab data. This model is fast, reliable, and interpretable, giving winemakers, marketers, and quality control teams actionable insights that can improve quality, profitability, and marketability. It is not about replacing human expertise, it is about enhancing it, providing an evidence-based tool that works alongside the centuries-long practice of winemaking and deliver consistent, better results. Thank you, and if you have any questions, I will take them now.